Hello, welcome to the Written Exam 2 practice videos. In these videos, we're going to try and walk all of you through solving every single question on the Written Exam 2 practice. But while we're doing so, we're going to try and explain all the concepts that we use in a manner that is clear, and hopefully by the end of all these videos, you will not only feel confident in solving any problem that is on these practices, but you'd feel confident extending any of the concepts to any other problems that we might throw at you, or even that life will throw at you. Okay, so let's get started. Question 1 asks, find the eigenvalues and eigenvectors for the corresponding matrix. Now, this is a 2x2 matrix. The time that it should take to do this problem is going to be very short. However, I am going to explain Laplacian expansion and how that would work for a 3x3 matrix, so bear with me if this video is actually a little bit long. Okay, so let's get started. Remember, the definition of an eigenvalue comes from this equation. AV equals lambda V. This is an eigenvalue. And this is our original matrix. And V is eigenvectors. So just by looking at this equation, it's not clear how to find eigenvalues because the only variable here that we actually know is A, and we have one equation and two unknowns. So we actually can't solve this just from this equation, but this is a good thing. This equation is very good to know, and you should memorize it. How do we find eigenvalues and eigenvectors? Well, first off, we need to start with finding the eigenvalues. What you do is you take this determinant of A minus lambda I sub n, and you set that equal to 0. By doing this, you can solve for the eigen. By solving this equation, you will find the eigenvalues. So let's perform this equation. I sub n is the identity matrix, and A minus lambda I sub n is simply A with all entries on the diagonal subtracted, or having lambda subtracted from them. So we have determinant of 3 minus lambda, 4, 1, 6 minus lambda. Now we need to find the determinant of a matrix. So for a 2x2, this is very simple, but for a 3x3, it's less so. So what I'm going to do now is go over a technique called Laplace expansion, which talks about how to find the determinant of a 3x3 in the most efficient way possible. So let's consider a matrix, 0. Actually, let's just do A, B, C, D, E, F, G, H, I. Okay? When you write down a matrix and you think about doing Laplace expansion, you should think of also constructing an invisible grid over the matrix that looks exactly the same shape, but it has entries that are positive or negative. And you want to lay out the positive and negative entries in an alternating pattern, just like this. So what we can do is we can sort of move, never mind, I can't do that, sad. All right, so you can think of moving the positive and negative entries over the matrix. The next step of Laplace expansion is to choose a row or a column to expand by. Let's choose the column this. So let's choose, that's not a column, that's a row. Let's choose this row, the first row. What you would do is for every entry in this row, I would say, like for A, you expand by every entry inside the row or column that you choose. So when I expand by A, I take out all entries on the row or column of A, and I multiply A by the sign of A, so plus 1, and I multiply that by the determinant of all the entries that are left. So E, F, H, I. I preserve the order. Now, what I would do is I would add B. So the next entry I would expand by would be B. And I would expand by the column that B is on. And so I would get, and let me erase that. So then by expanding on this, I get B times negative 1. As you see, there's a negative here for B. and you multiply that by the determinant of all the remaining entries. So that is D, F, G, I. If this seems complicated, it kind of is, but when you do it a bunch of times, it actually becomes very, very simple and second nature. And then we would also do this with C, so it'd be C times 1 times determinant of D, E, G, H. Now, the power of Laplace expansion is that this is a very simple and extendable method to use on even greater shape things, because if you have a 4x4, then you could think that, like, if you expand by any column, you would get 4 entries, and those are multiplied by the determinants of 3x3s, and you could apply Laplace expansion to those, and it sort of iteratively scales itself downwards. The other powerful part of Laplace expansion is, what if entries of A, B, and C are 0, right? What if I gave you a matrix where instead of A, B, and C, I had 0, 1, and 0. If you expand by this row, suddenly our determinant becomes literally 1, negative 1 really, times the determinant of D, F, G, I. And that's a determinant of this entire matrix. It becomes very, very powerful when there are entries or rows or columns that have mostly zeros in them. Okay, now there's a lot of reasons why Laplace expansion works, but that would take too long for this video. So that's all I'm going to cover on Laplace expansion. Hopefully it's clear how you would, if you were given this problem, find the eigenvalues and eigenvectors for the corresponding matrix, but you were given a 3x3 matrix to work with, or even a 4x4, you wouldn't be totally lost on how to do it, and you would hopefully actually know how to proceed with finding the determinant. All right, so for a 2x2 matrix, we can apply Laplace expansion. We could choose a row and then expand by all the columns, and the determinant of a 1x1 matrix is simply the entry inside the matrix. So Laplace expansion does work for a 2x2, but it's much more simple to just remember that the bottom diagonal, product of the bottom diagonal subtracted, or the product of the upper diagonal is subtracted from the product of the lower diagonal. So 6 minus lambda 3 minus lambda minus 4. That's our determinant. Now we can use our normal algebra to solve this. So we get, what is it? 18 minus 9 lambda plus lambda squared minus 4. So we get lambda squared minus 9 lambda plus 14. And can we think of factors that would solve this? I believe we can. However, if we couldn't, we would have to remember the quadratic formula. Which I am going to look up right now just to make sure that I do not get it wrong. Yep, so it is x equals negative b plus or minus the square root of 4 b squared minus 4ac. That's where I looked it up. 2a. Okay. This is, despite the fact that I didn't remember it fully, it's pretty easy to memorize as well, but yeah, in case you need it, might be helpful to know it, but again, you just need to factor this because this equals 0. So this is actually just lambda minus 7, lambda minus 2. So we get lambda equals 7, lambda equals 2. So what we're going to do is we're going to label them in descending order. Notice how I already ordered them such a way. So lambda 1 equals the higher number, the highest number. Lambda 2 equals the next highest number, and there's no other entries. So it works out. So now what we do is we have one eigenvector for every single eigenvalue. That is always a rule. There will be a unique eigenvector for every eigenvalue. And what we're going to do is for lambda 1, we're going to find our eigenvector. Okay, so how do we do that? Well, what we do is we take the kernel of a minus lambda 1 times in. For those of you who haven't taken linear algebra, the kernel of a matrix is roughly all entries that, when multiplied by the matrix, are 0. Result in the 0 vector, specifically. So let's calculate this out. We get 3, 4, 1, 6, which is our original A, minus 7, 0, 0, 7. And this gives us negative 4, 4, 1, negative 1. And because we're trying to find the kernel, what we can do is we can sort of envision that we're multiplying this by some vector, x1, x2, which gives us the 0 vector. Okay, so what we can do is usually for eigenvalues and eigenvectors, for finding eigenvectors specifically and finding the kernel here, you can just tell by inspection what the values of x1 and x2 are. Sometimes you can't, and there's a method for doing that with kernels, but in the overwhelming majority of cases, you can just use inspection to figure out what values of x1 and x2 would work. If you didn't, you could use a system of equations to sort of help you. So 4x1 plus 4x2 equals 0. We also know that negative 1x1 plus x2 equals 0. And so if we solve the system of equations, I hope that you would get that x1 is equivalent to x2. So we can assign one of these values, one of the x1s or x2s, the arbitrary value of 1, and we fill out the rest of the eigenvector that way. So 1, 1 is an eigenvector of A. However, there's one more step. We need to normalize every eigenvector that we report. Now, one handy thing about eigenvectors is that 1, 1 is an eigenvector of A, right? But the span of every eigenvector is still an eigenvector. And more importantly, the span of this eigenvector, which we can label as V. Oh, what's happening? The span of this eigenvector, which we're going to label as V1. So AV1 is still an eigenvector of lambda. So it's still an eigenvector with the exact same eigenvalue. So what we do by standardizing our eigenvectors is we set their magnitude to 1, and by doing so, it makes them much easier to just report and compare. That's the only reason we do it. Now, how would we set the magnitude of an eigenvector to 1? Well, we would find the unit eigenvector, and all that is just v1 over the v1. So this would get us 1 over root 2, and there is nothing there. And that is it. That is v1. Okay, now let's work on v2. Hopefully now that I've explained the whole process, this should go a lot faster. Okay, so I'm going to drop a lot of the excessive notation that I've been using, and I'm just going to do this very quickly. So we get 3, 4, 1, 6, minus 2, 0, 0, 2, which gets us 1, 4, 1, 4. So we know that x1 is equivalent to negative 4, x1 is equivalent to x2. No. There we go. And by knowing this, because if x1 is equivalent to negative 4x2, then that would make them equivalent. Yes. So then we know that our eigenvector can look of this shape. And then we can normalize it, and we get -4 over root 17, 1 over root 17. That is our second eigenvector. Now, one small note when normalizing eigenvectors. One way you could think of this, so what I did here is I assigned 1 to x2 because I know it was the smallest, and so I get a easier one to scale. But if I assigned 1 to x1, then I would have the form -1 and 1/4. And normalizing this is a little bit more annoying, just mathematically wise. So remember that you can always scale a vector and then transform it back into the unit vector, and it'll make no difference on the actual vector that you get. That's like a little trick I would recommend. So you would just transform this back into -4, 1, and then you would get our unit vector. Okay, but yeah, that's the whole problem. This took a long time, but hopefully if you practice this enough, you should be able to do this in hopefully a minute or less. And yeah, good luck on the rest of your studying.